Hey everyone, and welcome. Have you ever really stopped to think about how the food you eat becomes the energy you use to, well, do everything? Today, we are cracking the code on one of the most ancient and essential processes in all of life, glycolysis. This is the story of your body's own amazing energy factory.
So let's kick things off with a question I think we can all relate to. You eat a cookie, right? It's delicious, and then, a little while later, you feel a boost of energy. But what on earth happens in between? How does that sugary goodness transform into fuel your muscles can actually burn? The answer is this incredible 10-step chemical dance.
The name itself actually gives us a massive clue. Glycolysis comes from two Greek words, glykos, which means sweet, and lysis, which means to split. So at its very core, glycolysis is literally the art of sugar splitting. It's a beautiful cascade of reactions designed to break down a glucose molecule and unleash the energy locked inside.
Okay, to really wrap our heads around this, we're going to use one main idea for this whole explainer. Think of glycolysis as a clever biochemical investment. Seriously, your cells are these incredibly savvy investors. They know that sometimes you've got to spend a little energy to make a whole lot more.
So first things first, before we get into all the nitty-gritty details, let's just get that 30,000-foot view. What's the overall game plan here?
As you can see, the whole process is broken down into two main acts. Act 1 is the energy investment phase. This is where the cell puts some energy in up front. Then comes Act 2, the energy generation phase, and that, my friends, is the big payoff. It's super simple, really. One glucose molecule goes in, and at the end of the show, we get two pyruvate molecules and a tidy little profit.
All right, let's zoom in on that first phase, the investment. Just like any smart business plan, the cell needs to put in a little seed money before it can expect any returns.
So here's the strategy. The cell takes two molecules of its main energy currency, ATP, and uses them to get the glucose molecule ready for what's coming. Think of it like priming the pump. This initial investment makes the glucose unstable and reactive, perfectly setting it up for the main event, getting split right down the middle.
Our first investment happens right out of the gate. An enzyme called hexokinase grabs that glucose molecule, and bam, it uses one ATP to stick a phosphate group on it. This does two brilliant things. First, it charges up the glucose, and second, and this is key, it traps it. That glucose can no longer escape the cell, it's locked in and ready for processing. Now, fast forward a couple of steps, and we get to maybe the most important moment of this whole first phase. A big-name enzyme, PFK1 for short, spends our second ATP molecule. And this is the point of no return. Once this happens, that glucose molecule is fully committed. There's no turning back. The investment is officially locked in.
Okay, deep breaths. We've spent our two ATP, the investment has been made, and now it's time for the part we've all been waiting for. It's time for the big energy payoff.
And here it is, the glycolysis, the split. That 6-carbon sugar which we so carefully prepared gets chopped right in half. We're left with two separate 3-carbon molecules. Now, the most important thing to remember here is that from this point on, everything that happens twice. It means all of our profits are about to get doubled.
So, interestingly, the first part of our return isn't actually ATP. As these new 3-carbon molecules get shuffled around, some high-energy electrons are stripped away and get picked up by this special carrier molecule, turning it into NADH. You can think of NADH like a rechargeable battery. It's holding on to all this energy that the cell can cash in for even more ATP later on down the line. And there it is, our first direct cash deposit. In this step, we generate our very first molecules of ATP. And because we have two of those 3-carbon molecules to work with, we make 2 ATP right here. We spent 2, we've made 2 back, we've officially broken even.
And now for the grand finale. In the very last chemical reaction, an enzyme called pyruvate kinase swoops in and pulls off the final phosphate groups. This move creates our last 2 ATP molecules and leaves us with our final product, 2 molecules of pyruvate. That's a wrap. So let's do the final accounting, shall we? We invested 2 ATP at the start, but we generated a total of 4 ATP in the payoff phase. So 4 minus 2 gives us a net profit of 2 ATP. Plus, we walked away with those 2 high-energy NADH batteries. For a 10-step chemical process, that is a pretty solid return on investment. But wait, the story isn't quite over. What happens to that pyruvate?
Well, that all depends on the circumstances, whether the cell is running a marathon or a full-out sprint.
So what's next for our hard-won pyruvate? Well, the pathway now arrives at a critical fork in the road. And the direction it takes from here, it all comes down to the presence or absence of one single molecule: oxygen.
If there's plenty of oxygen around, we go down the aerobic path. The pyruvate gets shuttled into the mitochondria, the cell's powerhouse, to be completely dismantled for a massive energy payout. But if there's no oxygen, the cell pivots to the anaerobic path. It quickly converts pyruvate to lactate. Now, this doesn't make any more ATP, but what it does do is recycle those electron carriers we need to keep glycolysis itself running at top speed. It's all about getting fast energy now. And when would this happen? Well, think about an all-out sprint. Your muscles are burning through energy so fast, they just can't get enough oxygen, so they switch to this anaerobic mode for quick fuel. Our red blood cells use it all the time because they don't even have mitochondria. And on a more serious note, it's also a process used by some tumor cells and can happen during a heart attack when an artery gets blocked.
Now, you'd imagine that with a pathway this fundamental and this powerful, you'd need some pretty tight controls, right? The cell can't just be burning sugar for no reason. It needs a very smart regulation system.
And what we see here is that brilliant control system in action. It's a classic example of what we call feedback inhibition. It's so cool. When the cell has tons of energy, high levels of ATP itself actually act like a stop sign. The ATP molecules will literally go back and bind to those key enzymes we talked about, like PFK1, and act like an off switch, telling them, hey, we're good for now. Take a break.
So when you boil it all down, it's this incredibly elegant supply and demand system. When cellular energy is low, the pathway is running full throttle. But when energy levels are high, the pathway puts on the brakes. This makes sure the cell never wastes a single precious molecule of glucose. It's just so smart and so efficient.
So there you have it, an investment, a split, and a payoff. This intricate 10-step dance is happening trillions of times every single second inside your body, just to keep you alive and listening. It really makes you stop and wonder, doesn't it? What other incredible, tiny engines are firing away and powering you right at this very moment?